Okay, picture this. How is it actually possible to be simultaneously stretched into a single atom noodle, completely burned to a crisp, and somehow safely cross into an alternate antiverse? I mean, how's that even possible? It sounds like pure sci-fi, right? But according to the bleeding edge of physics, this paradoxical nightmare could literally be your reality if you ever took a dive into a black hole. Welcome to our explainer on the ultimate cosmic death trap. Today, we're diving into the absolute greatest battlegrounds in modern science. We're talking about the epic war between classical general relativity and quantum mechanics. And it's all playing out right there on the dark, warped canvas of a black hole. Section 1. The ultimate cosmic death trap. So to even begin this hypothetical journey, you actually have a pretty vital choice to make. Stellar versus supermassive. Basically, you gotta choose your doom. Now, you might think a smaller black hole is safer, right? Well, actually, it isn't. If you choose a stellar black hole, one with a mass of maybe 20 of our suns, the gravitational gradient is so insanely sharp that you'd be violently torn apart millions of miles before you even reach the edge. So to survive the initial approach, we absolutely have to choose a supermassive black hole. These monsters are millions of times heavier than our sun, and because they're just so incredibly huge, the tidal forces at their edges are actually gentle enough to let your physical body pass through intact. Well, for now, anyway. Section 2. Anatomy of a black hole. Okay, so as you're approaching, the first major boundary you hit is the photon sphere. This is this wild spherical boundary with literally zero thickness, where photons of light are trapped in a dynamically unstable circular orbit. Imagine this. If you were floating right there at that boundary and looked straight ahead, the light reflecting off the back of your head would orbit the entire black hole and hit your own eyes. You would literally see the back of your own head. Crazy, right? But it's highly unstable. Just one tiny nudge from a random particle of infalling matter, and that light either escapes out into the void of space or spirals straight down into the dark. Moving just a little bit further in, we hit the ISO, which stands for the innermost stable circular orbit. Now, in standard Newtonian physics, you can orbit a mass at pretty much any arbitrary distance. But here, in the extreme warped curves of general relativity, this is the absolute closest you can safely orbit. Inside the ISO, any infinitesimal perturbation, like literally even a microscopic bump, in your perfectly stable orbit collapses entirely. You're sent spiraling inexorably inward, and there's no coming back. Let's take a closer look at the core of a static, uncharged Schwarzschild black hole. Check out the event horizon right there. That's the absolute boundary, defined by the Schwarzschild radius, where the escape velocity finally exceeds the speed of light. Nothing, absolutely nothing, escapes that line. And right there in the very middle is the singularity, where density just becomes infinite. Once you cross that green line, the event horizon, there are zero paths through spacetime that lead anywhere but inward. I absolutely love how one of our sources captures this terrifying reality. Quote, "Trying to escape a black hole from the inside is like trying to stop Tuesday from happening." End quote. I mean, wow. So the absolutely crucial point here is that inside the event horizon, space and time warp so severely that the singularity is no longer a physical place in space. It literally becomes your inevitable future. You cannot avoid it any more than you can avoid tomorrow. Section 3. Spaghettification and the firewall. All right, now this builds into a massive clash of theoretical titans. We are literally pitting general relativity against quantum mechanics to determine your ultimate fate. And depending on which branch of physics you ask, your gruesome death looks very, very different. So, if classical general relativity is the undisputed boss of the universe, you experience what physicists actually call spaghettification. It's driven by extreme gravitational tidal forces. Basically, the gravity pulling at your feet becomes vastly stronger than the gravity pulling at your head. At the very same time, you're being horizontally compressed. The end result? Your body is violently stretched vertically and squeezed horizontally. As you fall closer to the singularity, you are reduced to a string of atoms literally just one particle wide. You become the ultimate cosmic noodle. But wait, quantum mechanics tells a completely different, scorching story, and it's known as the firewall. Here, the danger is driven by high-energy quantum mechanics. The incredibly extreme environment right at the event horizon causes pairs of particles and antiparticles to violently split apart. And this continuous microscopic splitting and colliding, it generates an impenetrable wall of immense heat. So instead of being smoothly stretched out, the infaller is instantly burned to a crisp the exact millisecond they touch the horizon. So, spaghettified or completely incinerated, believe it or not, physics still hasn't definitively decided.
Section 4. Secrets of the Kerr Singularity.
Now, because real dying stars actually spin, real black holes have to conserve that angular momentum, meaning they spin too. This introduces the totally mind-bending Kerr metric. Just notice how the addition of spin changes literally everything. A standard Schwarzschild black hole, that's a static dead end. But a Kerr black hole, it rotates. It has both inner and outer horizons. And the immense centrifugal forces actually smear the singularity out into a one-dimensional ring, a ringularity that theoretically offers a potential passage. But before you can even attempt that passage, you've got to navigate the ergosphere. This is a crazy region just outside the outer horizon, where something called frame dragging occurs. The black hole is spinning so violently that it literally drags the very fabric of space-time right along with it. To just stand still in the ergosphere, you would actually have to travel faster than the speed of light in the exact opposite direction. So yeah, here, standing still is physically impossible. You literally have to rotate with the void. But let's say you manage to navigate that, right? And you pass directly through the center of the spinning ringularity without hitting the lethal ring itself. The math reveals something absolutely incredible. The antiverse and the Carter time machine. The equations actually suggest that passing through the ring could expel you into a manifold where the gravitational radius becomes negative. That means gravity becomes repulsive, an antiverse that violently pushes you away rather than pulling you in. Or alternatively, navigating the incredibly complex geometry around that ring could place you on closed time-like curves, theoretically allowing you to travel backward in time. I mean, no way, right? Section 5, the black hole information paradox. So, the legendary physicist Stephen Hawking made a truly monumental discovery about this whole process. Step 1, the black hole consumes your physical matter along with all of your unique quantum information. Step 2, the black hole doesn't actually just sit there forever. It slowly leaks energy via what we now call Hawking radiation. And step 3, over trillions and trillions of years, the black hole completely evaporates into absolute nothingness. But that brings up a massive issue. If the black hole disappears, is the information that made you, lost forever? This right here is the paradox. A core, unbreakable rule of quantum mechanics called unitarity demands that information can literally never be destroyed. But Hawking radiation is basically just random thermal noise. It seems to carry zero information away from the black hole. So, if the black hole is entirely gone and the radiation is completely blank, where on earth did your data go? Well, one genuinely wild theoretical solution to this is called black hole complementarity. So the crucial point here is that your information might actually be cloned. One copy of you falls in and is destroyed, while another copy is simultaneously scrambled and radiated outward. Now, I know what you're thinking. Quantum rules strictly say you cannot clone information. But because no single observer can ever see both the inside and the outside of the black hole at the exact same time, the laws of physics are technically preserved. Both realities basically exist, depending entirely on who is actually watching. It's a real head-scratcher. Physicists are working around the clock to try and rescue our understanding of the universe from this paradox. And here are a few other potential solutions they've come up with. First, the page curve, which suggests your information is kept safe and just eventually released super late in the radiation process. Then there's the baby universes theory, rooted in Einstein-Cartan theory, which proposes your data is actually funneled into a brand new, completely detached universe. And finally, the holographic principle. This one argues that your information never really fell in at all. It was just permanently encoded onto the two-dimensional surface of the event horizon, sort of like a hologram. So, it all leaves us with this. When the final black hole evaporates into the cold, dark void of the extremely distant future, will the universe remember you were ever here? It's a truly stunning question, and honestly, one that leaves us incredibly hungry to uncover the ultimate secrets of our quantum universe.